and actually thanks all of you for being here or for attending this short talk. Before starting the actual talk, I just want to give you knowledge and recognition to everybody in the group in Milano. We are quite a diverse and I would say nice group, and a mixture of several competencies. Today I will focus on a work which was mainly performed by Chiara, one of our PhD students. She's actually going to graduate at the end of this year. Then there is Martina, and the pixel-like picture is Nick. So we have started this type of activities, I would say 2.5 years ago, so we're still young in this field. Nonetheless, we are trying to push it as much as we can for several reasons. So I think there is not much need for an introduction about the importance of mineral dissolution and precipitation. So I'll just leave the slide hanging here. Everybody in the room knows the importance of this. What I would like to focus on in this presentation is what happens at the micro nanoscale at the solid fluid interface. So only to that particular scale, and to try to get a closer look to that, where the key element is associated with the evaluation of focusing on pure dissolution, whatever it means, pure dissolution in this case. Okay. So, and the key idea is to work and analyze or quantify, first observe and then try to model in some way dissolution plates by considering pure calcite in contact with some liquid, with some fluid. So, why are we interested in that? Well, we start for determination of reaction plates. Some cases people can work, or there are quite a lot of work with batch experiments to ascertain reaction rates. And in some cases, reaction rates, either kinetics or equilibrium, they are then used as obtained from batch experiments in, for example, transport models, trying to mimic these kind of reactions across porous systems. Or what you can do is you can take a closer look at the surface of the mineral, and you can somehow measure or come up with the distribution of reaction rates by, let me say simply, for the moment, having an idea. This is simply a transect across the story model of the surface of the mineral by measuring in some way the roughness of the surface of the mineral. You measure the roughness of the surface of the mineral several times, okay? And you come up with several pictures in time of topography. You can use those differences in topographies and come up with estimates of reaction rates. The key element which at least started to capture my attention was a color map. And the color map, because at least in my view, I've been working quite a lot with geostatistical analysis of hydraulic conductivities or other hydrogeological quantities at different scales, looked like a heterogeneous field. And more on top of that, to me, it piqued my interest because it looked like a strongly heterogeneous field, which might be captured through some of these stochastic approaches that also together with Xavi and Dani, we have developed over the course of the year. So that's what started my interest in this part. And the general idea was to come up with a way to transfer some of the knowledge that we had at some other scale, with some other quantities, at such a small scale, come up with, first of all, the capability to observe it, and second of all, some capability to model it from a stochastic standpoint. That was the key premise. Okay? So, this huge heterogeneity is related to several intrinsic sources of variability of the system. And you can have steps, impurities of the crystals, screw dislocations, point of line effects, and all of these contribute to a highly heterogeneous distribution of reactive sites. Therefore, there is always the need, or what we felt was the need to start with a closer look first ourselves, because we had never done it. Okay? I know that other people or other researchers have done it, but we had never done it. Take a closer look at what happens at the crystal surface, and then to come up with an ensuing interpretive approach. We are not the first ones trying to come up with a description based on some statistics of reaction rates. However, at least what we found in the literature was that there were analyses which were then associated with some analysis of the frequency distribution, and from that frequency distribution, maybe to come up with some extreme values with this generalized extreme value model. But there were no analysis, at least from what we saw, for example, on the degree of spatial correlation of these reaction rates at such a small scale, and on a, let me say, established interpretive model of this. And so we tried to work on this part. And so the idea is to structure the presentation by simply enumerating some mechanism of calcite dissolution, description or synthetic description of the experimental equipment that we have in Milano, the atomic force microscope, and then come up with measured observed values and some statistical modeling approach, and then maybe some future perspectives or some future work that we are doing. So there are several mechanisms which are associated with different evolution of the topography of the surface of the crystal, focusing on calcite. The type of mechanism can be roughly classified, or the type of patterns of the surface of the crystal can be roughly classified as a function of the saturation condition, far or close to equilibrium, according to several types of mechanisms. Far from equilibrium, you can observe several mono or multi-layer etch pits. Typically, they have a shape of rhombohedral shapes. Then you increase the saturation, and you have a combination of multi-layer etch pits with a different shape, mostly triangular from what we have seen, and a process or phenomenon which is called strap retreat. You have several terraces in the crystal, while at close to equilibrium conditions, mainly the pattern at the surface of the crystal is governed by dynamic step retreat in this case. I'm focusing, so we worked at far from equilibrium and at close to equilibrium conditions. Okay? And I'm focusing on showing you something or some results that we obtained at far from equilibrium conditions. Yes?
What is a step retreat?
Step retreat, it is as if you have several terraces which evolve in time. I'll show you some pictures of those with the dynamic evolutions of those. Okay? In this. So, the key principle in order to come up with a spatial distribution of reaction rates, in this case of dissolution rates, and by spatial distribution, I mean that we are talking about an area of investigation which is of the order of 10 microns with a resolution of something like 10 to 11 nanometers in this case. And by spatial resolution, I mean you have something like 500 by 500, I know it's 512 pixels along each direction. So at each point, you have an observation of the topography of the system. You take observations at two different times, and then you simply subtract them. This is the molar volume of the site, and then you come up with a map of dissolution rates. Then, with this map of dissolution rates, you can do some analysis. We prefer to do a statistical analysis by analyzing jointly reaction rates and their spatial increments. Why their spatial increments? Simply because at the very beginning, I started by trying to apply geostatistical approaches to the analysis of this kind of heterogeneities. We always work with spatial increments. And then you always need to ensure consistency between the statistical distribution of, let me call it parent variable, and its space and or time increments. Where by increments, I mean differences of values of that particular quantity at a given data. Okay? So we wanted to analyze jointly the variable and its corresponding increments. So this is more or less a synthetic description of the apparatus. So essentially you have a piezoelectric scanner, lever, a tip, and the sample is here. Okay? Then you have a detector. The tip in these experiments that I'm showing you is in contact mode. We are starting with non-contact mode experiments, but they are not working for the moment. Maybe I will show you the results next time. But it's not like they're not working. We are starting with the non-contact mode. And the key idea is that whenever you have the cantilever scanning the surface along these directions, then due to the atomic forces, van der Waals forces, essentially you have a deflection, and from the signal of deflection of the cantilever, you have topography of the system. And then you can also have friction maps, which enable you to see, I would say, more or less clearly, different regions in the system. This is a pit, and this is like a terrace, like I was saying, in the system. So these are the type of images that you have. And just to give you an idea, this is the sample. Okay? It is just a pure calcite, just to give you an idea of the size of the sample. And this is Chiara holding the sample in the lab. Okay? It's just another view of the system, just to give you an idea about the fluid inlet. We use as a solution, we simply use, at least in these experiments, milky water. And the volume in the cell is around the order of 2 milliliters in this case. So we tested 2 settings. I'm going to show you only one, and the third setting is under development. The first setting is basically static conditions. So you have the sample, water in contact with the sample, static, no movement, and of course, in time, with the dissolution of calcite, well, you tend to saturate the liquid film. Okay, I'm not going to show you examples in this case. It mimics, for example, what can happen in a dead-end pore in a system, in a porous system. Then,
when did you take this of the 1/3 of the sample?
sorry?
So you have 1 layer of
Yes, which is about less than a millimeter. Then,
So it will saturate if it is static?
yes, of course. It saturates very fast. Nevertheless, when we started, we wanted to start with simple things, just no movement. Then we wanted to engineer movement, just to mimic what happens in flowing pores. Well, it turns out that engineering movement is not that easy in this case, because you also need to have to acquire clarity of the images, and when you increase the velocity of the fluid, it means you increase the Reynolds number. I will show you some effects on the clarity of the images. So here I actually devised 2 types of, let me call it, flowing conditions. Okay. And I'm going to show you some results related to this particular setting, and simply at the end of the seminar, at the end of the talk, just how we are calibrating the second setting to start with the next type, with the next phase of the experiments. So in this case, right, we simply have a syringe pump, okay, and we fill the flow cell, and then we let the fluid static until a first scan of the system is completed, and it takes approximately 6 minutes, at least with the current apparatus that we have, to scan the system. After 6 minutes, you replace completely the 2 milliliters of water. So it is like as if you were using an intermittent flow rate, which is evaluated like this. Okay? So, this is the kind of experiments that we are doing over time, and that I'm going to show you. Over time, we take images of the surface, and you can see this is after 26, 22, 52, and after 1 hour, just to see some evolution. You can see multi-layer pits spreading. in this area over time, some monolayer pits and some terraces in the system. Sorry, what is the blue? The blue is a multilayer pit in this case. So it's a pit which spreads, and it's multi-layer because it involves multiple layers of the crystal. Okay? So this is the temporal evolution where I think you can see the evolution of all of those terraces that I was mentioning here. And this is the pit which evolves. Look, the line, different colors correspond to different times. You can analyze these images and you can come up, of course, with estimates of the rate of spreading of the pit by taking some averaging of these distances over time between two different locations of the pit. So you can also have, of course, a description, a dynamic description of the topographic surface of the system, including the different different processes which take place. Sorry, the different topological elements which take place on the surface. So in essence, what you do is at a given time you can recognize two regions in the system. One region, at least in this case, one region which is a pit, and another region which is basically a terrace. Therefore, if I do an analogy with a typical aquifer system or a typical porous medium, it's like having two regions, let me say, with different permeabilities. Here you have different properties of the system. Okay? That's why we wanted to apply the techniques that we are usually employing in the description of aquifer system, also to the description of these kind of systems. Therefore, we conceptualized the system as a composite domain, and the key element was to describe the two regions in terms of random locations of the regions and random distributions of the properties within each region. Of target variables within each region, where by target variable I mean reaction rates. Of course, the primary variable is the topography inside each region. And that's how we build our statistical model of interpretation, which is nothing more, nothing less than what we typically do in the representation of some aquifer systems with geostatistical approaches. So, you come up, like I said, you come up with image or with a map of local reaction rate through subtraction of topography maps, which are taken at two different distance intervals, well, set apart by 6 minutes, each. In the map, when we analyze this variable, of course, you can recognize two regions. One region with high reaction rate, and the region with high values of reaction rate is clearly associated with points in the system which transition from a terrace to a pit, for example. You have a high reaction rate in these regions, and the region with, let me say, moderate or low reaction rate is characterized by it's associated with everything else in the system. If you then construct, you take this map, you come up with a sample probability distribution of the data, you come up with, let me say, in this case, you have two regions with a bimodal distribution. Okay? Normal enough, I would say something like this. Normal, I mean usual enough, not normal distribution, sorry. Then, of course, we want also to characterize this kind of distribution so that it is compatible with the probability distribution of the increments associated with given lags. So you can construct increments associated with given lags. This is just an example of spatial increments associated with 3 lags normalized according to the size of the system. And you can see several things in this kind of distributions, which I'm going to comment in details in just a few minutes. So you can see, first of all, 2 peaks here simply because we have 2 regions. Okay? Then you can see a central peak and 2 lateral peaks in these distributions. Not only that, you can see that the distribution of the increments depends on the lag at which you take the increments, which is of course normal.
The distribution of the rates is centered at zero. The mode is zero.
This is, sorry, it is removed from the mean. I'm sorry. It is the fluctuation of the reaction rate. I'm sorry. This is R prime. Sorry, I forgot to tell you. You're right. I'm sorry. I took out the mean. Sorry, of course. So as always, we analyze the fluctuations with respect to the mean. I'm sorry. And then you have the distribution of the increments. The distribution of the increments transitions with lag, which is also logical. The point is to have then to come up with an interpretive model which can take into account transitioning of this distribution. Some people call it scaling of the distribution with the interval, with the increment, which means that you have a scaling of the mean. Sorry, the mean is always zero for the increment in this case. You have a scaling of the variance, and you have a scaling also of higher order moments of those distributions, depending on the distance, which is also nice, because if you can come up with a unified theoretical framework for this kind of distribution and the distribution of the spatial increments, then you might hope to scale the whole probability distribution of your variable.
In this increments, you separate also the case of region A and B.
Oh, they are all included. No, they are all included. Of course, they are
Doesn't
included.
matter.
Of course, they are included. Of course, they are included in this case.
No,
I'm
the
taking
left, yes.
everything here.
In the left, yes, but in the right one also.
No, of course, everything. You take everything. Okay. Now the question is, what kind of model can we use to reconcile the two types of observations? So we can do it, of course, for several time intervals. So at several times we have maps of rates. Then the point is to see whether or not we can interpret them with, let me say, the same structure of the model. And then maybe we are going, well, I would say yes, we are going to have parameters which depend on time. And then we need to interpret the temporal variability of the parameters of this distribution, and maybe in 10 years, we are going to be able to link this temporal distribution to the different type of processes and topologies associated, and degree of irregularities, so etch pitches of terraces which are taking place in the system. Okay? So, well, we started by noting. We started with the distribution of the parent variable. We saw that it is bimodal, and we said, well, let's try a simple model. Let's try a mixture of two Gaussians, for example, which is okay. It's reasonable enough, I mean, as a model. Then, in order to come up to identify or whether or not it is a mixture of two Gaussians, instead of simply doing it blindly, of course, the first idea was, let's say, for each time, to somehow separate the two regions, identify them, analyze the data within each region, check whether or not they are distributed in a Gaussian way. Of course, if the system is Gaussian, so if the variable is Gaussian, its spatial increments must be Gaussian. If they're not Gaussian, then it means that your Gaussian model is not good. Okay? Well, it's the sum of two Gaussian variables. Okay.
Only if it is multilayer.
Of course. Well, there's no way to show multi-Gaussianity. Okay, of course. But there's no way to show multi-Gaussianity. You have to assume that because, well, you have to assume ergodicity, but that's okay.
There is a big discussion there.
No, definitely. So forgive me if I did not use the proper terminology in that.
No,
yes, I agree.
No, I agree. You insist, I will insist. I agree. What we all assume, and we know,
I agree.
there has not been a single case where multi-Gaussianity has survived.
I agree. I totally agree. With this. I was not insisting.
Still we use it.
I just agree. Okay. Note that in some cases, when you go into this, when you analyze the variables in these regions, then the increments are really not Gaussian. They are heavy-tailed. They have tails which vary with the distance, with the lag at which you take the increments, and then we developed a different model for that one. Let me go with a simple one. Okay? So then, just to show you what it means by having a Gaussian model, so that the system is conceptualized, so our random field is conceptualized as a multimodal random field, which is identified, in this case it's bimodal, so we have a random indicator function, and these are classical distribution, these are classical development associated with the probability density function. In this case it's a bimodal random function. Nothing new, of course, in this case. Then you come up with a bimodal mixture of the of these fields. Again, nothing new in this case. You can come up with raw moments of order Q, mean variance, nothing in this case. The point is that after this, you can clearly see that a Gaussian mixture model of this kind depends on a bunch of parameters, on 8 parameters. So you have the mean of the two distributions, standard deviations. Of course, you need the degree of spatial correlations of the two distributions, and then the proportions, and then, of course, at least the range of the indicator function, which is also a random field in this case.
Sorry.
Yes.
Can you explain? I don't understand. I was expecting only 5 parameters. So the fact that we need 8 is.
Well, because these Gaussian fields we want them to be spatially correlated. So, like we do in classical geostatistics. So we have a bimodal distribution of spatially correlated Gaussian random fields. Okay?
Why?
Because we want to analyze whether or not there is a spatial correlation. There is a internal spatial correlation within each random field. Within it,
Okay, no, I understand the reason. My question is, why, given this model and given that you have given an explanation for the biparameter structure and the double issue of Gaussians, which you, I mean, to me, I think you were implying that they were associated with the 2 different regions.
Within each region, I have correlation. I have spatial correlation. So this is the correlation function of the rate within region A, and this is the correlation function of the rate within region B.
Oh, okay, sorry.
Okay. No, maybe I didn't.
No. It's very clear. Sorry, it was.
No.
Okay.
No problem. Okay. So now we need to develop a probability distribution also for the increment, which is compatible with this one. It turns out that it's not that difficult. Well, here I prepared a couple of slides simply to show that it is not the only case where you can see distribution of increments which are characterized by those central peak and 2 lateral peaks of the kind that I have shown before. We had analyzed previously some data. These are vertical profiles associated with neutron porosity that were measured were recorded in an oil field, along a well in an oil field, and these are distribution of increments in different labs. This is the sample PDF of the original data, and these are sample PDFs of the population of the increments. And we saw this kind of behavior in several data that we analyzed. The key point being that at some points we could, even for other variables, distinguish these 3 peaks in the distribution of the increments. And to be honest, in this case, we use the model which basically ignores the distribution of these two lateral peaks. We were not using a Gaussian mixture model. So we started deriving from the Gaussian mixture model the probability distribution function of the increments. And you come up with this kind of expression. I don't care about whether the expression is long, short, or whatever. The point is that in this expression there are several ingredients. Okay? There is the correlation function, the covariance function of the indicator that we consider in the system. Then, of course, there are the parameters, the correlation function of the field, let me say the field A and of the other field, and of field B. This part here, we did some studies, of course, on this one, which I'm not going to show. If you're interested, of course, I can show them. This part here governs the peak, and this part here, this term here, governs the location of the symmetric lateral peaks. Not only that, the distribution depends on the degree of correlation between the 2 points at which the increments are taken, which means that naturally this distribution changes depending on the lag that you take. Okay? So, in essence, we came up with this interpretation, which hopefully could transition, or which is compatible with the nature of a, at least in this case, bimodal. We hope it can be extended to multimodal, but for the moment, for bimodal. So, starting from a bimodal field, bimodal Gaussian field, then you can come up theoretically with a distribution of spatial increments, which has all the features of the data that we have seen. And just to give you an idea about how well it can interpret the data. Of course, we developed a procedure to come up with an estimate of all these parameters. I'm not going into the details of that procedure. And these are the experimental data and the symbols, while the curves, the solid curves, are the resulting model interpreting the data at different times. And we could see that they could interpret the evolution of all these. Note that the structure of the model is always the same. The only thing which changes, of course, are the values of the parameters in time. And naturally, you can see that the distribution of the probability density function of the increments are actually capable of transitioning from one scale to another. Now, of course, you come up then with estimates of the model parameters. And so you have an estimate of the proportion, an estimate of the correlation scale of the bimodal indicator, functions, of the end of all the parameters, correlation scale inside each field, which stays inside each of the two regions, which stays more or less constant in time, and where is it? And of course the variance. We are still working on tying the temporal variability of these or lack of temporal variability of these quantities to the actual processes taking place in the system. For the moment, we saw that they are consistent with what we see in terms of data. How to link them with the different type of processes, we still have some work to do in this case. Okay? And we also tried, just to go back to another scale, so to permeability, for example. These are famous experiments which have been published in 1998. It's a block of, this was a topograph. It's a block of topograph along whose faces several air permeability data were collected, where air permeability was inferred because the measurements were fluxes and entropy and pressures. So these are permeability maps, air permeability maps on one face with different resolutions of the measurement of the tip. And what was interesting to me was that they were essentially showing you a system composed by, let me call them two geomaterials, two different types of materials. And so we said, well, why don't we try to interpret these also these with the model that we developed. And it turns out that we can actually do it. These are the data, and these are the interpretation in the system. So we have nice interpretations of also this kind of data. It means that at least the theoretical framework is flexible enough by jointly considering increments and the variables with different quantities and different scales. This said, we are working now on, so what I showed are primes, so fluctuations of the reaction rates. because for those samples, we had not the capability or possibility to set up a reference plane. Now we are working on that, and we did actually work with inert masks with gold and titanium in this case, and we can actually come up. Chiara is actually working quite a lot on setting up this type of experiments with the mask in order to come up with absolute reaction rates. So we will be able also to include the actual reaction rate and the actual topography, and not only the fluctuation which is obtained after detrending the data, as is usually done in these cases. The other thing that we are working on is trying to establish continuous flow during the imaging. And by continuous flow, we work with high precision syringe pumps. And what Chiara is doing is to work on this kind of analysis. So these are 3 images taken at 3 different velocities. It means 3 different values of the Reynolds number. And you can see that depending on the Reynolds number, which is evaluated in some way, depending on the value of the Reynolds number, the same quantity, okay, it's viewed with different degrees of, let me say, granularity, coarseness. So these are bad images, and good images, the one in the middle. So there is an effect also the velocities on the capability of the atomic force microscope to provide us images which can identify features on the surface. And we came up with, at least for the moment, a range of Reynolds numbers within which it is actually feasible to obtain a nice compromise between having a non-zero velocity, continuous velocity and non-intermittent velocity like we had, and the capability of observing features in the system. And by observing the features in the system, we at least thought of considering the mean spreading rate of the pits, and find the region of values of Reynolds number where that measurement is actually not influenced by the Reynolds number. And hopefully we are going to start experiments with this new equipment. And for the moment, Chiara is doing some analysis with reference calibrating the structures in this case. So it looks promising, and I hope that next time I will be able to show you also some analysis and ensuing interpretation of these other types of information. I would say that I can stop here, and thank you very much. And any questions? I will be more than happy to try at least to say something intelligent. Thank you.
Please. Question, yeah, and you very nice presentation, by the way. And you mentioned that you measure relative rates using the setup that you've done so far. Can you say something, or can you deduct maybe from your last experiment something in terms of absolute rates and what it means in terms of changing the solution composition? Because I mean, then you're injecting stepwise mode, so you put some solution in place, and when you are doing a scan, right, and then you change the solution again, and so on.
Yeah, we measure relative rate because there is not much else that we can do without a reference mask.
Yeah.
That's unfortunately the point with the first one. But of course, since we were interested in increments, we were interested in fluctuations, we thought it was good enough at least to start working and interpret that. In terms of so I don't understand what you mean by changing the solution.
Because I mean, the solution is staying put for some
for
minutes,
6 minutes.
and so in that time, the solution composition is changing. Is it changing a lot?
No, it's not. Okay, no, it still stays well below saturation. So it still stays within the limit of very low saturation. Okay, we did some tests with, by considering the time that it takes to go, let's say, above 0.5 or even very,
So you
very
may
high.
consider that you're more or less
That
the same already in
yeah,
terms of the
yeah.
solution.
In that case, in these experiments, I think so. Let's say that we are quite confident about that.
No, but so far you're using, so when you finish the experiment, you analyze the water.
Yes.
And
No,
now you
that's
have
what-
also
that's
the
what we
capability of analyzing it, but not now. in the
No,
future.
that's a different story. So what Shad is referring to is that we just acquired a new instrument. This is, let me say, atomic force microscope. Now we have a new atomic force microscope with also Raman capability. And so we still don't know how it works, okay? In the sense that we're still, there are still people training in using it. And hopefully within next year, we're going to use the combined atomic force microscope and Raman capability also to come up with, let me say, real-time measurements of chemical concentrations in the solution. Technically, it has been done by a group. There has been a paper. We submitted a paper about just to show that we have the capability of doing that. I did not do the measurement. I did not take the measurement personally. Okay. However, we have participated as a group in this paper, which has appeared last week, just to show that there is also the Raman capability. Was I clear?
Yeah, excellent.
I think that was basically that was follow up the question, no?
Yeah.
How can
Sorry.
how can you relate what you see with what it's actually there?
You can measure the water, the composition of the water, then
Yes.
there's a whole.
Yes, the key idea is also to couple the Raman capability in the near future. First, we want to solve these issues.
Who's doing it?
Huh?
What is this apparatus?
In my department.
No,
Yeah.
the one that you're
It is.
saying.
It is.
Already,
Yeah,
okay.
it is already there. So it's pretty new because it was delivered last September, October. So between October and now, it is still in the testing phase. So.
I would say that Andreas would be a firm veteran, but perhaps you know him, that has been working with this Raman technique for at least 5 years.
Okay.
Doing set of atomic force microscopy also, but also working with vertical interferometry.
Oh yes, we worked.
Well, the paper you showed first slide, fish.
Yeah, it was.
Fellow was working with Andreas.
Okay.
Did you say light interferometry?
Vertical interferometry.
Yeah, we did some work with Damien Deval. With Damien.
This group are.
Yeah.
They are using the technique for analyzing the, let's say, the in-situ changes in the etch concentration.
Okay. So, like I said, for the moment we are still testing it. But so actually, when I visited the first time, when I visited some time ago Strasbourg, there was I didn't know Damien.
Yeah.
And he showed some images, and that's where I saw the colors, and I said, "Oh, this is like a conductivity field." And so he said, "No, it's something else." And so I started asking him to explain, and then it was a few years ago, and that's how it started. So.
Then regarding your results, for instance, in the experiment you have been working with, you are working in certain conditions of chemical solutions. Like
Yes.
The experiments basically were close to equilibrium or near to equilibrium. And all your statistics were applied under these conditions.
Yes.
So the point is that then, depending on where you are, let's say the delta G region, then you will have to apply different statistics all the time.
It might.
In the sense that this interpretation is used for a certain, let's say, certain value of delta G, let's say that observation state of the solution. If you change that, then you will have to change all the analytical, let's say, exercise.
Maybe yes, maybe not, in the sense that I agree with you. Okay, of course it is valid only for these conditions. I'm hoping that at least the theoretical framework, so multimodal distribution, not sure whether Gaussian or not, and joint analysis, so the methodological framework, joint analysis of the distribution and the associated increments still can provide some insights. Okay. I don't know how to factor in the distribution, also the saturation variable for the moment. It is something that, of course, we need to study. But yes, I agree with you. It holds only for this.
Yes, but I would say that mainly the main point is that all these correlation factors, you basically get some values or some correlation, that correlation is going to be changed in another condition.
It might.
And
Yes.
it's like somehow what you are working, or let's say that your ultimate goal would be to replace what the reactive transfer modeling by using the reactive area, reactive surface area. We want to basically to remove this concept and then to basically apply all this knowledge for basically for modeling in the reactive.
Well, I don't want to remove anything. I want to complement something. But yes, I see the point.
Whatever you showed there.
I see the point.
Fisher would give, let's say that the direction is that.
Yes,
Basically, the reactive surface areas are there, and it's very useful, but it's a black box.
I see the point, and yes, I agree. That's
Finally,
exactly.
what you are basically doing is that you are open this, let's say, this black box, and you are introducing another parameterization
Well,
that can relate these changes in reactivity compared to, let's say, the big factor of
oh yeah.
the reactive area.
Another thing that we started doing actually was to try to relate, but it's still ongoing. We try to relate we are trying to relate the parameters of these distributions to the main parameters controlling kinetic Monte Carlo simulations, for example, in that case. And if you use kinetic Monte Carlo, you see very similar patterns to this. And the point is, can I really find a link between parameters that you use in kinetic Monte Carlo and parameters that you use in this type of stochastic descriptions? That's what another area that we are exploring. So yes, I agree.
Yeah, because what you say, actually, I think you need some sort of mechanism for the reason why you have this dissolution, this terraces, let's say. I don't know whether you have already a clear idea of that, or is it just an observation?
Yeah, for the moment it's an observation, at least in my mind. I think that maybe there are some other people who have done this for longer than I have done and they have clear idea. So I'm just saying what we are seeing and the way that we are trying to interpret it.
I must say that I don't think that this issue that you are discussing is so critical, because in reality, the time scale over which you have changes at the given changes in concentration at a given point in space is so much larger than the time that the characteristic pattern of these reactions that you can assume. I mean, I think your assumption is fine in reality. I mean, in a given point in an aquifer,
Jesus, which assumption? Because I made a lot.
the assumption that you guys are discussing now, that how does the saturation...
Okay.
It doesn't change.
Okay.
I mean, it does change over centuries, but not over historical time.
Well,
Not by the experiment maybe for
No, in an experiment, yes, but I mean in reality.
Yeah.
In an aquifer, you have the water.
Yeah, but the point is that the experimental observations, yeah, I agree, I think it's very good, and what you say makes sense, and it doesn't change a lot, but you want to translate some kinetic parameters at the end to a set of chemical conditions that need to be related to saturation index, of course, but then you need to know in the experiment where you are, and then in nature, yeah, you need an even point in space, and the changes are not so big, but you need to know what race, what values to apply to given set.
And but for that, I think the experiment does it.
Yeah.
So but anyway, no, I have two sets of questions, and all of them involve your team.
So I can sit down.
No, I have to discuss further. The first one, I thought I would not ask. First image, when you show that, oh shit, this is crazy, you have to do it by tiny different. But then I realized that the light interferometry, the wavelength applied is several hundred nanometers. You could not go beyond a solution of 1 micron.
yeah, okay.
So forget it. I mean, the type of feature that you're observing.
No, it's this, I mean,
By the way, if you want to do that, we have the best interferometers in the world. I attended and you visit. So you guys enjoy it if you want.
well, I think that we break several times.
And they are the best. That is all that they are sending it to the Russians, to the Americans, to the Chinese, to everyone is dying to either. Anyway, so that was my question. So you're happy with the resolution?
For the moment, I'm happy. So,
You mentioned 10 nanometers.
no, 10 micrometers. No, sorry, I didn't, I misunderstood you. No, 10 nanometers.
Okay, so you must use atomic force.
No, you can do it. I mean, they use interferometry to the same resolution.
But you can have a resolution of 10 nanometers in the wavelength is 600 nanometers.
They measure the signals. They
My,
types
underst-
of features.
my understanding is that at least from the work that I saw from Damian, that he can go to the 10 nanometers. That was my understanding. To the tens of nanometers. That was my understanding. I didn't study all the details of the instruments. So, but that was my understanding. So.
Yes.
However, for example, what he does, or at least the experiments that we analyzed with him, so he had the sample, there was the sample, it was in contact, and then you had to take it out and measure the surface, and then to place it back in, which means that you could not place it exactly in the same position. It means that you could come up with only average reaction rates and not full spatial distribution. While the original variable, which is something else that we are trying to do, the original variable is not the reaction rate, it's the topography. So with Damian, we studied we applied the geostatistical analysis of the topography, because with the vertical scanner interferometer, that was the best that we could do, at least with the experimental conditions. Now, of course, the rate is the difference between two topographic surfaces. So, in my mind, the original variable that you measure is the topographic surface. So the point is to combine the statistics of the topographic surface with, and from those to come up with the statistics of the rates, which is not that easy. Okay? And this is what we are trying to develop right now. So to start directly from
Which takes me to my original question, the one I really wanted to do, and the one that again I already. I remember when you presented, I think you remember, because the question when you discussed your AFM experiments. What I learned from that lecture is that the solution takes on the bit edges by increasing the size, which is consistent with what you showed. I mean, you have two types of things. One will
There isn't a step for treatment.
There is also-
Feature in the surface, and then there are steps that are faster than others. But it takes everywhere.
but
Just that there is an heterogeneity of rates.
So the point is that it is actually quite high from what I have seen.
no, wait a minute. This is not what you explained, and this is not what he showed. What he showed is that you have two types of phenomena. At least, sorry, not what you showed. I don't know what you showed. What I understood from your presentation is that you have two types of phenomena. One that occurs at the edges of the peaks, and this is the advance of the peak, and there are huge dissolution rates there. And another one that occurs where you have a more or less homogeneous, of course, it's never homogeneous, there is no homogeneity in nature. But you have a relatively flat surface where you have, yes, a little bit of dissolution, but this is, it's hard to tell the difference, but in any case, much smaller. If you don't have absolute values, all we can say is that it is much smaller. So I say that because to me, this is a clear description. And if I were to describe it stochastically, I would say, okay, how do those work? And when you show the several pictures, you can see them moving.
Yeah.
Instead, by trying to blend in one stochastic model two different phenomena, it fits the data very beautifully. It's very spectacular, and it is very nice for other things. Not for permeability. This is another discussion that we discussed another day. Isn't it too complex for something that you could describe in terms of, say, okay, I have two sets of phenomena, and then I separate one process in areas where it is flat, one process in areas where it is, where you have this.
Okay. I can tell you my answer and then you can add on your. My answer is the following. I might agree, however, you just don't know where the nucleation of the pits starts arriving. It means that, at least the way that I conceptualized it, you actually have two random fields, the pits and the terraces. That's why.
Yes.
Yeah, therefore, it is conceptualized as a composite system with two random fields. So you have the random, and in this case, you can use it. Otherwise, if you want to treat them separately, first you need to identify where the pits are, separate them from the terraces, and then perform the analysis. So it's a two-step system. Okay. Otherwise, so if you do it like this, you can even, okay, I don't want to go that far, but maybe you can generate stochastic realizations in space and time of the evolution of the surface. I don't know, in 10 years, maybe. Was I clear enough?
I understood everything you said, from which I reached the opposite conclusion of what you did. So that's why I am a bit confused.
That's okay.
What I'm saying is that if the two mechanisms are different, probably the geochemical parameters are probably then different. I don't know. This is why I am asking you. You are the unpaid.
From Andrea, what Andrea has been on for many years, but I mean they are not in they are linked. So when you look at the interpretation, interpretation is that you have these etch pits, where you have this nucleation of steps, and then you have this step trade. So you have a very localized fast dissolution rate at the etch pit, which creates these steps, and then these steps refill. So you will have a very small zone with a large dissolution rate, which propagates into a larger zone with a smaller dissolution rate, but what it counts is you sum everything. So it's not that the pits do that work and they're not important, doesn't work. So you have these steps that normally have they switch.
Of course, but in terms of describing the geochemical mechanism, I will come up with the first principle rate law. This is what counts.
No, sure.
I mean, because in the end, what you want, I mean, not what you want in this description, but what the reactive transfer person would want is a rate law.
Yeah, well, let's put it like this. What I would like to do, or to be able to do, is to find a way to relate, for example, the parameters of the distribution or the variability with time, or the actual value of correlation scales of the parameters of the distribution of the different quantities to the mechanisms that are taking place. I still haven't done it yet. What I hope to do is something that is along these lines. So it's not that different from what you're saying. It's just a different way of tackling the same issue, I guess. Maybe I misunderstood you, but of course I agree with what you said. I mean, of course. So we are trying to do it in a different way. That's it.
No, it's not that necessarily. I very much.
No. We're just trying to go even deeper in the research. Yes.
Yeah, how do you describe it?
Yeah. So we were able to find some relationship between the correlation scales of the indicator function, the evolution in time of the correlation scale of the indicator function, and the average speed of the spread of the edge pits. We saw that there is some correlation. Now, how to explain it exactly? Well, we are still not there, to tell you the truth. Okay, but we saw that there is some correlation.
And the other point is to, as Jordi said, do the same thing at different saturations.
Yes,
so how it changes as go from equilibrium.
Definitely. We did the same analysis actually with close to saturation with the static fluid, and yes, you have different distributions. Okay. However, you can still interpret them with the same within the same theoretical framework.
And I think maybe just looking at the different saturation states, it helps you make a mechanistic model, if you will, of everything. I mean,
yes.
Why does it change?
No, I totally agree, and that's why I'm hoping that with this new system, by considering the flow condition, we can even keep the saturation constant.
Yeah.
And that was one of the key points on this. But otherwise, you really have not much control. Either you are
Yeah,
after
yeah.
a while.
Conditions are changing during the experiment.
Exactly. So yes.
Sorry. Basic question. So is this mineral sample surrounded by an impermeable boundary, or is it also dissolution occurring to the lateral side of the
No. Well, let's put it like this. The sample is 2 centimeters and something. We focus on 10 micrometers. So of course it is contained. However, well, it's not too much influenced by but of course, yes, it is contained. And actually, to be quite honest, to come up with, let me call it a good area, okay? Where a good area, by good area I mean where you can spot an edge pit. It takes Chiara time. So it's not easy to come up with.
Well, that's the advantage with vertical hydro from
You have a larger
field of view.
Yes, you have it. You have a larger field. I agree. Like I said, we were not able to come up with, because of the way the sample is treated, so that's why we decided to go into this one.
Also, say that one aspect for the carbonates is that the transport limitation, the influence of the transport in the reaction, that's also an important factor.
Yeah.
Contributes to this saturation state of the solution. I would say that your residence time is very, very large in your experiments. And then that's, you have a lot of influence of this diffusion transport effect.
Let's put it like this. Like I said, according to the measurements that we took of the chemical composition, we are still far away from equilibrium. Of course, you have a variability. Yes, I agree. Within these 6 minutes, yes.
Great. Second question. So when you consider the experiment, with the flowing water, do you expect any influence of the instrument in the flow?
That was well, let's say it was these images like here. So you have different values of the Reynolds number, and this is the type of images that you get. So it's really an influence of the velocity.
Would you say it's also influenced by the velocity of the instrument sampling the
It's a combination of the two. It's a combination of the two. Actually, I do not remember. I think I need to ask Chiara, but I do not remember if these were taken in contact or non-contact mode. I'm sure. Chiara, are you listening? Are you online?
It was stopped.
It was stopped. I don't know. Maybe not, because there was a department meeting in Milano, so she was not sure to. However, it also depends on whether or not the tip is in contact or non-contact mode. Okay. Maybe this one is in non-contact mode, but I'm not sure. But so yes, you can have an influence also, that depending on.